Hello, let's talk about parallel circuits and the characteristics of such circuits. Before, we noticed that when you have a circuit in series, you can connect all the elements in a consecutive fashion, such that you have that you have a capacitor, that you have a resistor, that you have an inductor. But now we're going to do a parallel configuration of the elements, such that you can have an inductor and a capacitor in parallel or a resistor and a capacitor in parallel. Then we want to analyze how the system behaves, and ultimately we want to see how to apply the concept. Okay. So as we saw before, the elements in parallel are pretty much the same as we saw for DC circuits. So we have elements going from the top or high voltage line to your low or ground line. And the difference between this circuit and DC circuit is that the source is AC instead of DC. Everything else pretty much the same. So since we have AC power going to the circuit or AC voltage, we have to compute the impedance instead of the total resistance. And in order to compute the impedance, we have to compute the reactance of each element. We know that by now. Okay, if you want to compute the current, the electrical current going through each branch, we use the current divider rule. That we saw before that in a circuit in parallel, the voltage through each line is the same, but the current is different given the what is the name? Given the rating or the nominal value of the passive element. Okay, so obviously it's going to be different if you have a 100 ohm resistor that if you have a 1000 ohm or 1 kilo ohm resistor. So the difference here is that you're going to have current division or in parallel. The voltage is going to be the same. Voltage 1 is going to be the same as voltage 2, but current 1 is not necessarily going to be the same as current 2. So for DC circuit, which we applied the Kirchhoff law, in AC circuit, we know that depending on the element, it's not as simple because there's some phase shift. And now what we're doing is adding and subtracting waves, which if they have different phase, then it's going to be pretty tough to add and subtract. And we saw that before. If you want to compute this current, please go ahead and look at the current for parallel circuits. You have to use the square root and the magnitude of the current to know what's your real component and your imaginary component. Okay? So if you want to find the current through each leg or each branch, you simply have to find the current through each branch using the current divider rule. So for I1, the current through branch 1 is going to be the impedance of the second element times the total current that you have from your source divided the impedance of the first element plus the second element. Okay, this is only for two elements. If there's more than two, then these formulas have to be extended. So, for example, find the current through each branch. We have a total current of 20 amps. Suppose that this is measured with a multimeter or with a oscilloscope, and initially there's no phase shift because, say, it comes from your connection at the wall or from the equipment that you're using. There's no phase shift, so the initial point starts right at 0. And then there's a resistor in parallel with an inductor, and they're giving us the total reactance. We know that this guy is 2 pi frequency times inductance. Since we don't know the frequency for this particular point or this problem, and we don't know the inductance, they're giving us the total reactance of the inductor, and the inductance of the resistor is simply going to be the resistance. So what is the current through each leg? we use the current divider rule. We know that the denominator is always going to be the adding or the sum of both elements. So we're going to have 3 ohms plus 4 ohms at a phase shift of 90 degrees because it's an inductor. Okay, and then multiplying, we're going to have 4 at a 90 degrees phase shift. This is the same here and here, times 20 amps. For multiplying phasors, you simply multiply the magnitude, which 4 times 20 is 80, and you add up the phase shift. 90 plus 0 is 90. So we already have the denominator. For the denominator is 80 amps at a 90 degrees phase shift. For the denominator, we simply have to find the magnitude, and this is square root of 3 squared plus 4 squared. We know that this is square root of 25 equals 5, and that's what we have here. And to find the angle, we simply do tangent inverse of what the imaginary, which is 4, divided the rule, which is 3. 4 divided by 3, tangent inverse of that is going to give us 53.33. At this point, it's very simple. We just have to divide 80 divided by 5 is 16, and 90 minus 53 is 36.87. So we already have the current through the first leg. The current through the second leg is exactly the same. The only thing that is changing is the numerator. The numerator is exactly the same. Look, is in reactance or the impedance of the resistor plus the impedance of the inductor. We already have that here is 5 phase shift of 53.13 degrees. The only thing changing is the numerator, which now is going to be 3 ohms at a 0 phase shift times 20 at 0 phase shift. So 0 plus 0 is 0, and 3 times 20 is 60. We know that by phasors. Divided by 5, this is going to be 6 divided by 5 is 12, and 0 minus 53.13 is negative 53.13 degrees. So by now, we computed the total current. Please remember that since we're dealing with AC circuits, it's not the Kirchhoff's law where I total equals I1 plus I2. This is not true. This is different than I1 plus I2. In order to compute this, we have to do the magnitude with the square root, etc. So when you have a circuit in parallel where your initial wave has frequencies that are varying, so that your frequency goes from one value to the next value, but it's not a sudden change, it's an incremental change, kind of like they're showing here, that goes incrementally changes the frequency. The response of each passive element is different. We saw this before. The response is exactly the same that you have in series because the response depends on the element, not on the circuit. The combination of the elements is what makes the response of the total circuit, and that's where we want to see next. We know by now that the reactance of the resistor is completely uniform at any frequency. The reactance of an inductor is a straight line with positive slope because this slope is basically 2 pi frequency and inductance. The only thing that is changing is frequency. Everything is the same, therefore you have a positive slope. And we know that this is inversely proportional because we have 1 divided by 2 pi fc. F is changing the frequency, therefore we have this curve that we already know how to compute. So if you were to compute the total response, it's going to give you something like this. For the few or for small frequencies, you're going to have an inductance response. It's almost linear. Then it's going to go to the maximum at the peak frequency, and the peak frequency is computed by 1 divided by 2 pi square root of inductance times capacitance. And then it's going to start decaying in a capacitive fashion. So in a circuit with parallel resistor, inductor, capacitor, from small frequencies to large frequencies, you're going to have this behavior. For the first smaller frequencies, you're going to have inductance. For the middle portion of the frequency range, you're going to have a resistive response. And for the last portion of the high frequency side, you're going to have a capacitance response. And the total impedance is going to be minimum at the maximum frequency and the smallest frequency. For example, let's say we have a circuit with a resistor that is 220 ohms and an inductance that is 4 millihenries. If you compute the reactance, you already know that this is the formula to compute it. So this is 2 pi times frequency varying times 4 millihenries. So 4 millihenries is the same thing as 4 times 10 to the negative 3 henries, or 0.004. These are the same thing. Okay, so evidently the reactance of the resistor is going to be uniform, 220 ohms for any frequency, but the reactance of the inductor is going to be increasing when frequency changes. At this particular point, they're not giving us any frequency, so you can use kilohertz, which is pretty common for low range applications. So we can go from 0 to 40 kilohertz. And you know that up to 20 kilohertz is what we can hear with our as humans. This is what we can, the noise that we can hear, the music, everything goes up to 20 kilohertz. But that is for a mechanical wave. For an electric wave, they can be transmitted and moving at much higher frequencies, megahertz, gigahertz, like for cell phones, etc. Now, in terms of F1, we know that this is the resonant frequency. We compute resonant frequency by saying that the frequency that we get by resistive reactance is the same response that we get by the frequency at the inductance reactance. So in this particular case, we have that what we say that this is frequency. We know that we want to find a specific frequency where, given the value of the inductance and the resistance for this particular circuit, because notice that every circuit could have different values of reactance and inductance. So for this particular circuit, the frequency of resonance, the resonant frequency for the configuration will be the resistance divided by 2 pi inductance. And this is the same as 220 ohms divided 2 pi times 0.004. And that is 8.75 kilohertz. So if you go to Excel, we have that. Let's do this all over again. We said the resistor is 220 ohms. The inductance is 4 millihenries. And pi is 3.1415. We're gonna get a frequency range of from 1 to 1,000 to 20,000, because 20 kilohertz. We don't want to start from 0 because we might have to divide by frequency, and we don't want to divide by 0. So we're gonna go all the way to 20. There you go, that's enough. So the next thing we want to do is we're going to do the total impedance, and we know that to compute the total impedance, we do this formula: Z for impedance is equal to 1 divided the square root of 1 over the resistive reactance plus 1 over the the reactance because of the inductance squared, square root of that. Okay, so let's do that first. We're gonna do Z total equals 1 divided by, here we're gonna have the square root in parentheses, sorry, the square root in parentheses of 1, we probably want this whole thing, so yes, of 1 divided by the reactance, which is 20. We're gonna have to compute the reactance because of the inductor first, so let's do that here. The reactance because of the inductor is going to be a function of frequency, has to be here. The reactance because of the inductor equals 2 times pi, lock that cell, times frequency times inductance, lock it that cell, enter, and double click here to extend to the bottom. Excellent. Then we have, let's do the total reactance now, which is equal to 1 divided by square root of 1 divided by the resistance, the reactance of the resistance, lock it, squared, plus 1 divided the reactance of the inductance, squared, close, and extend. So if we plot frequency versus total reactance, we should have a graph like this where it converges at 220 ohms because of the resistance, which we saw it was the maximum. And if we go back to our presentation, we see that indeed we should get convergence around 220 ohms. And now the point of inflection is where the reactance of the resistance is equal to the reactance of the inductance, which is this point. So in other words, R equals 2 pi LF, where if we need to find it, if we do that, we're gonna say, okay, let's find our F for our resonant frequency. Let's say F1 equals 220, lock it, divided by, in parentheses, 2 times pi, lock pi, times the inductance, lock the inductance. 8,753, so 8.7 kilohertz, and that is exactly what we get, 8.75 kilohertz, 753. Excellent. So now the next thing we need to do is nothing. They asked us to compute the total impedance, and we have done that here. Now the same thing we want to do for the parallel RC circuit. So what we have to do now is instead of an inductor, we have a capacitor. Therefore, the reactance of the capacitor is 1 over 2 pi frequency times capacitance. We can do that. And the same thing, we're gonna know that when the response of the resistor is the same as the response of the capacitance, the reactance of the capacitance, then we can have a resonant frequency. So F equals 1 over 2 pi RC. And here's the computation right here. And in terms of finding the total reactance, we have this formula. Or the formula that I like better is a little simplified. Just be careful when you plug it in. You can go either way, but I like this one better, which is 1 over reactance of the resistance squared plus 1 over reactance of the capacitance squared. This reactance with of the resistor does not vary with frequency. This does vary as a function of frequency. So you probably have to compute this one first, and this is going to be homework to compute this curve using Excel. So the application of parallel circuits is very common for industrial applications and for residence or home applications. So if you go to if you live in a house, if you go to panel board, you'll see that you'll have something similar to this, where from the transformer outside your house, there's line 1 and line 2. Each line has total maximum voltage of 170 volts, or RMS voltage of 100, around 120. And this one, line 1 has 120, line 2 has another 120. So in total, line 1 and line 2 will give you 240 volts. Okay, but not every application requires 240 volts. The reason is back in the 30s and 40s when they were setting up the grid for electricity, a lot of places already had a 120 volt outlet and their appliances were at 120 already. But a 240 is much more efficient and 480 is even more efficient. So when they tried to go up to 240, they said, okay, some people already had 120 volts, and now that we want to go further distance with the grid, let's go ahead and use 240 for other stuff. So they kept both, and it's very simple. From the transformer, there's going to be line 1, there's going to be line 2, there's going to be neutral, and of course there's going to be a ground. Okay, so line 1 will be 120, and line 1 and neutral will be 120, and of course ground. And 240 is going to be line 1, line 2, and ground. So for 120 volts, you don't have neutral. For 120 volts, you have neutral. For 240, you don't have neutral. So the neutral bar is right here, and is eventually connected to the ground bar. And then, so as I said, for 220 volts, you have both neutral and ground, but you can combine L1 and L2 to get 240 volts. So evidently, do not work with this unless you're certified or unless the power is off. So you do not have to work with this at all, because this board, the spinal board, can have rating after 30, 40 amps, and even 1 amp is pretty dangerous. So if you are not working with electricity and certified, please do not try to work with this. But here's to show you the application. So evidently, as you see, L1 right here coming from this line this is a contactor. Then we have L1, L2. This is the whole copper bus for L1 and L2 to be conducted. So if you have L1, a fuse of 20 amps, we have L1, then we have neutral down here. So let's follow the neutral. The neutral is going to be all the way at the bottom to return to close the circuit. This will be where we have ground and our multisim. And then L1 is going to be, of course, there's a fuse here. So if you have a lot of things connected, a microwave, an oven, a lot of things, then you're gonna damage the fuse. But notice, then you have parallel circuit. So these two voltage lines are going to be at 100, both of them. The current could vary depending on what you have connected to them. If you have a lamp versus if you have an oven, a toaster oven. Then here there's another contactor or a switch, and then you have this one in parallel. Then you have these two also in parallel. So this is the application of how to use circuits in parallel for AC systems. Now, if you notice, let's say they tell us that this configuration, this appliance, this electrothermal, this is electrothermal because it's turning electricity into temperature, into thermal energy. This oven is operating at 240 volts. So what they do is that they take L2, of course there's a fuse, and now the amperage is higher because it can go up to 12,000 watts. So they're saying, okay, there's going to be L2 and L1. Okay, notice L1 and L2, and then we're going to connect to ground. Right, this is part of the plug, but this will eventually go to all the grounds in your house that are connected to a rod outside of your house somewhere. Now the AC is also 240, so they're gonna need L1 and L2. L1 and L2. Okay, and of course ground. And then same thing for other rooms. Notice this is switches and or contactors, and then they're using L2 for a different part of the house. So L1 could go to one part of the house, L2 can go to the other type of the part of the house, and or if there is a building or whatever, they only need 120 for the lights. So there's a switch in parallel with other light bulbs, and this switch opens or closes or lets it's going to let two lamps be activated at the same time. So kind of like a hallway or something that you turn on a switch or turn off a switch, and then both lamps will turn on and off. This washing machine is 220 volts, for example. So you only need one leg, so leg 2 is okay. And then you're gonna have neutral connected to your ground, which you notice that here's your neutral going back to your ground. And they're saying, oh, there's a dryer that is 240. Okay, so they're gonna need L1 and L2. Okay, so L2 and L1 right here, and of course ground, and so on and so forth. So if you just notice that if it's 240, there's gonna be L1 and L2. If it's 120, there's gonna be only L1 and neutral.